guys, welcome back to Introduction to Computer Networks at NTU. Yeah, this is week 5, episode 10. Today we don't have special announcements, but let's continue going through the checklist or the rules about taking exams. Okay, so this is the exam 1 channel. Yeah, good morning to you all. Very good that you guys understand the distinction between SMTP and HTTP. One is to pull data from the server down. The other is actually to push emails to the server. So the data are going two different directions. All right, despite that both protocols are client-server based. So you see that they are common in a way that both are client-server based, but they differ also in the direction the data goes. All right, so let's come back to the exam 1 a little bit more. Yeah, so there'll be some questions in exams, in every exams that's related to the programming problems, the PAs, programming assignments. Okay. So you guys will be asked to log on to the PA servers individually. And to work on your own solution, each of you would receive your own account on the server. And the ID of the account will be your student ID. And there's going to be a default password to begin with. So please change the default password ASAP. Okay. And that account will be ready a day before the exam. Now, shortly after the exam, these accounts will be disabled again. And it will come back. They will come back until the next exam, where you need the ID to work on the PA-related problems in the exam. And when Polly says it's time up, okay, make sure you close your editor and the FTP servers or SSH sessions so that the something.go file or sometimes the something.txt files that you generated, the timestamps on them will not be later than the closing time of the exam. All right? So this is something extra related to the PA-related problems. And by the way, during the exam, you guys are allowed only 2 SSH sessions during the exam. So maybe one session for editing, the other session for testing, for running, checking whether there are syntax bugs or runtime bugs. Now, Polly added one more post yesterday, thinking that maybe it's better to let you guys know the entire flow of the exam. So here's the exam process in the chronological order. First, be in the Google Meet session by 10:20 on the exam date. If you can come 5 to 10 minutes earlier, that's even better because starting from 10:20, Polly will call through the list of the students, and when you're called, you need to show your student ID. So you need to raise your student ID up and close to your camera so I can see the photo on the ID. So I can match the name and your face. All right. And the exam will start shortly after Polly finishes the ID check. So this process is expected to take some 10 to 15 minutes time. If many of you come 10 minutes earlier, then I can do the checking earlier, and we may start the exam earlier. So the reason that I'm never sure exactly what time the exam will start is because of this process. Okay, I need to check your IDs. When the starting time is, so after I finish checking the IDs, I will try to find a better time to start the exam and inform you guys that this is the starting time. Okay, and when the time ticks to the time will start, Polly will announce that the exam begin. At that point in time, Polly will open the Google form up for submissions. Polly will also upload the PDF file which contains all the exam questions. Okay, in a PDF file to the channel. So this way you can quickly go through the PDF file and find the problems that you are more comfortable working on. You are more confident that you will receive full scores. Okay. Now, when the Google form is open for solution, make sure that you fill in the basic information. Yeah, I see questions from Luis. Yeah. Okay, Pingyu, that's a very important question. Yeah, so you probably never know how to change the password. So let me finish bullet 2, and I'll come back to your questions, Luis, Pingyu. Oh, Anthony, thank you. Yeah, there's a PSSWD command on SSH on the X terminal that you can use on all kinds of shell. Pingyu, if you have questions, feel free to ask, okay? So after the Google form is open for answer, fill in your basic information and submit the Google form immediately, because that way you will get an email containing a link to your form. So you will never lose the form, all right? So once you submit, the link will come back to the exam form normally, unless there's like a major internet instability, internet breakage. Okay, so if you fill the basic information and then submit and maintain a good internet connectivity, after submission, you will come back to the exam form and you can continue working on it. If not, you should get an email, okay, from the account you use to fill the form. And from that email, you will see a link to your form as well. Okay, and if nothing worked, it's still fine, because all you did is just filling in the basic information. You see, you did not lose much. Then you can start the form again until you get the email and you get the link back to the form. You see, it makes sense to do this. So let me come to the questions down here. One quick question: do the two S's we are allowed to use during the exam count per connection or per comment? Hi, Luis. This is per connection. So in one connection, there's usually a terminal there. That's one session. So you can type in arbitrary number of comments there. Write files in my computer and just upload them using the SCP. I see. But you have so for that SCP command, you have an xterm running, right? So that terminal, that command line box is one session. So you can have two of those boxes. Luis, is this clear? Okay, just let me know whether this is clear. And let's come back here. So there are 100 points to earn and 90 minutes only to answer the question. So you want to skim through all questions using the PDF file and start from the problems that you are more confident in. Okay. So see, the PDF file might help. And also the fonts on the Google form, to some of you might be a little bit small. So reading the PDF files might help also. No, Louis. You can use arbitrary number of SCP. But you are allowed only 2 terminal sessions. So maybe when you are doing the test run, you can show me how you are doing the SCP, how you are inputting the commands. You should be using some sort of external clients and connect to the server. And on the terminal, you type in SCP or you type in VIM to edit your file. Yeah, so that terminal is one session. 2 terminals, 2 sessions. So in each of the session, you can type in any number of commands. But you are restricted to keep just maximum 2 terminals simultaneously. So you can use one terminal to do the editing, the other terminal. Now I see that you don't do online editing, so you could edit on your file system and then SCP. Yeah. Exactly. All right. Good. And there'll be some bullet 4, 5, 6 are just Polly reporting or announcing this is halftime. This is 5 minutes to the end. This is 1 minute to the end. So you guys are more aware how much time you have left. The last is this. Polly will do a 10-second countdown. When there are 10 seconds remaining, Polly will count 10, 9. And when Polly started counting 10, it's time for you to stop and do the last submission. And it's not just the Google form you need to do the last submission. You want to close all the editors for the .go files. Or if you have you are editing some text files, you want to close all those as well. Okay. And so in the end, we might see that we end the exam a few minutes before 12:10. So 12:10 is not strictly the ending time of the exam. Okay, the exact ending time will be announced at the beginning of the exam. When I say when the beginning time is set, I will say what time, and then the end time. And when the time is at the beginning time, I'll open the Google form and upload the PDF file. That's how things go. All right, so during the exam, if there are any questions, feel free just turn on your mic and ask over Google Meet. It is also okay to just type up your question on the Google Meet session. There's a chat space there. So typing up questions on the chat space helps because other students might have the same problem, and if they see on the chat space that the question have been asked and answered, that will save us also some time. And the grades will be released approximately 2 weeks after the exam. Okay, because the part grading the textbook questions are easier, but to grade the PA related problems, it will take some time. Polly usually goes through your code and find out, in case it doesn't work, where the bugs are, and that's how Polly determines how many points to assign to your solution. All right, so that will take some time. And last but not the least, and once again, whatever you do, Polly won't judge you differently. All right. And Pingyu, if you don't know how to change the password, please definitely contact us. And Pingyu, the thing is that in the assignment number 1, you should see in the PDF description how to change the password. If you already forget about it, check it out again. Make sure that you know how to change the password. All right? All right, so you see that it's okay. If you have questions, you see Anthony answer the question, and each of us is trying to be understanding and answering each other's questions. Much like, for example, there's a question yesterday from Sam asking about assigning the port numbers, and later in PA3 asking about what does local host meant. What does 127.0.0.1 meant? You see that people, for example, Brian is trying to help again. Thank you, Brian. And also, ask us anything. So there was a discussion last week about VS Code extension, using VS Code extension to access the PA workstation, which has SSH. So one can actually set up a VS Code server on the PA workstation, and that will make editing and testing a lot easier for the Visual Studio users. So guys, sorry that I've disabled that, given that it's a little bit hard to trace who's in, who's not. And I've learned earlier that some of you guys might have never changed your default password. And we are actually broadcasting okay, what we do globally. So it's a security issue. Maybe next semester that I teach the course, I need to think of another way to make sure that the communication of the default passwords are more secure. But the semester has already began and the default passwords are distributed, and that's be careful, all right? And so thank you guys for your understanding. So use the usual way to upload, testing the code. It will be a little bit more time consuming. It's less convenient. As we know, security and convenience are usually two things that you don't achieve at the same time. Okay. Yeah. Usually when you need to be more restrictive, then it's more inconvenient. But between the two, and given the difficulty of these assignments, I think it's okay to trade off a little bit of trade off a little bit of convenience for safety. All right, so yeah, Pingyu. Yeah, the PA1 is set up for you guys to know all the basics accessing a Unix-based system. And that is the most basic form of accessing the system. But you see, as I was talking about what Caesar, Ivan, and Brian were discussing, you see that there are other ways of accessing the PA workstation. Exactly. That's great. Yeah. Brian, perfect. Yeah, that's something that I was also thinking about. Remember TLS? We use the public key crypto system to exchange keys to begin with. So I think next time we use the SSH public key logging. All right? Yeah, so I will be soliciting you guys' public key. And by the way, for PA789, particularly PA9, you'll be using pollys public key and private key for the assignment. And that's, again, for teaching purpose. Okay, so that set of public key, private key is for teaching purpose. Okay, great. Thank you, Brian. That would actually address the issue of maintaining both security and convenience. Can we do this still this semester? Yeah, let me think about it, Brian. Thank you. So for now, thank you for your understanding. And I hope that I cover enough of exam 1 and somehow sort of give you some sense of security, okay, less anxiety. And time to go on. Okay, so yesterday we started introducing the second application called email, and we introduced this protocol called SMTP, which works in 2 levels of hierarchy. It works in 2 levels of hierarchy, all right, and it works from Alice sending an email to its local server. It works in the second level between Alice's local server and the receiver of the email's local server. But it doesn't work between receiver's mail server to the receiver. And that was quiz 12 is about. Okay. Today we're going to continue talking about SMTP, but switch gear. So yesterday we talked about the architecture and we talked about the flow of communication. Today we'll talk about the exchange of the comments and the emails. Okay, so the first video is to show you how the email comments are being exchanged. So these email comments, you can think of them like In HTTP, we send request messages and we receive response messages. In the request messages, there are these header lines, right? In the response messages, header lines as well, and data. So these exchange of messages, you can think of them as the header lines, the comments, okay? And the email content itself is the data part. All right, so let's check out this email. It's to show you how the comments are being exchanged to establish connection and to send a particular email. All right. This is a very simple SMTP exchange. Let me explain the notation. S being the server, C here being the client. Now in SMTP, this is the receiving mail server, and this is the sending mail server. Once the TCP connection is established, the receiving side identifies itself first. 220 hamburger IDU, status code, status phrase. Client here then would in turn tries to identify itself as well. Crepus.friends, that's the identity. And hello here is the command to allow the server to know who the client is. And then server, status code 250, everything is fine. Hello, Crepus.friends. And then beginning from here, we start to see control message exchange. Client here needs to specify who the sender is and who the recipient is. So mail sender is Alice and mail recipient is Bob. So all capital here, mail from. All capital here, receive to. Okay, our special commands as well, just like the hello. So whatever comes after the columns are the mailer and the recipient. So server again are just saying, okay, good, I got it, 250. And from here on, this is the actual data exchange. Data, once again, a command. Email starts from here. Do you like ketchup? How about pickles? And it ends with a single line that has only a period. Okay, so the actual email message is only this short, 2 lines. Last is here, just to close. Okay, server will say, message accepted, everything is fine. Client then issue yet another command to quit the session. Server says, all right, goodbye. Very simple. To set up connection, to do the email exchange, and to close the connection. In the email exchange, there's the control message part and then the actual data part. And that is an SMTP message exchange among the client and servers. Let's try now to telnet to an actual mail server at port 25 and see what the server would send back to us. And then we could try to type in some of these comments out and see how the server responds. So let's go to the demo mode. Now let's try telnet to a mail server at port 25. Telnet, which mail server? Actually Googled up Gmail's mail server. The name is this, SMTP, how appropriate. gmail.com, 425. There we go. IP address being 64 something something. And this is a message coming from the server, 220. All right, so SMTP, gmail.com there is identifying itself. And then ESMTP, okay, it's saying more. I'm not quite sure what this is. Right, so E must be something and then SMTP. So this might be a special variation of SMTP, maybe the encrypted version, I'm guessing. So let's try typing up some of the comments. For example, hello, and coming from us.edu.tw. How about that? Great, seems to be working. 250. So the server is saying, ooh, at your service. That's really polite. All right. Then let's try the next comment we saw earlier, mail to. And let's have Gmail sending to pollys email address. How about that? What is this? 530, 5.7.0 must issue a start TLS comment first. So yeah, it does look like it's trying to establish an encrypted connection. So TLS, if you recall, is what? Transport layer security support. So I'm guessing this is probably the credential, the public key. So I'm supposed to send back the share secret key with the public key as the key to encrypt. But I don't know how to do that. So Yeah, let me try it again then. Playing dumb here. poly@ntu.edu.tw. Let's see. No, it's not accepting it. So I have to, yeah, so maybe recipient from, yeah, Polly's Gmail address. How about that? No, it keeps bugging me saying, okay, let's do start TLS. So that's issue this comment, start TLS, and see, start TLS. Oh, cool, it's accepting. That's nice. Ready to start TLS. All right, so then I suppose I need to send back the, I'm already out. So it seems that the establishment process there also has a time limitation. Otherwise, yes, and hacker might be able to hijack something that you have done in the middle. Interesting. So, hey, I got kicked out. So Gmail is a secure email service. Email messages are encrypted. Nice. Good to know. And so that was a demo of trying to telnet to a mail server, actual mail server. You could also try this yourself, maybe from the workstation. Okay. All right. So, yeah, there are a couple of mistakes. It should be like send from instead of send to, and receive to instead of receive from. So Polly made a few mistakes there typing up comments. There you go, Sherman. Yeah, mail from. Okay, good. Very good, Sherman. And now let's move on. In the next video, you will see in the first half, Polly tries to compare HTTP and SMTP again. But in the second half, you will see how the data part of an email look like. There's actually a protocol defining the data part of email. The data part of email is somewhat somewhat more complex than the HTTP responses data, although HTTP response data can be complicated these days. Okay, but anyhow, in email in SMTP, the data part, there's another protocol defining it. Okay, so. And just a few words about SMTP at the end. Once it sets up a TCP connection, the client there can use the connection to send multiple emails. So it runs just like the persistent connection we see in HTTP. SMTP requires text in ASCII code, very strict. And SMTP uses just a single dot in the last line, okay, to determine whether it's the end of the message. Now, if we compare SMTP to HTTP a bit more, they differ in multiple ways, but they are also similar in another way. So this is the first thing they're different. Yeah, the service sort of direction. HTTP is actually to pull objects down, but SMTP is to push objects out. Now, object here I meant email. They are similar in this way. Comments, responses, all these messages are in ASCII text format. But HTTP and SMTP are also slightly different in this way. Each object is encapsulated in a response message. So HTTP server there sends one object at a time, one object per message. But SMTP can send multiple objects in one message. That message is just having multiple parts. So for emails, that comes with an attachment, like a big PDF file after, here is the attachment, if there's anything wrong, contact me. So email, the original text at the beginning, and then additional attachments. They can be sent as a multi-part message. So multiple objects in one message versus HTTP. One object, one message. Mail message format. So there's yet another protocol that defines how the email messages should look like. So this will be the data part of the SMTP protocol message exchange. If you recall in the example earlier, there's the opening phase, some control messages being sent, and then comes the actual data before closing. So the mail messages here we're talking about is the content being sent in the data phase. All right, so these messages are not control messages for SMTP. So they are not SMTP. The mail message format is actually defined in another RFC. It's another protocol. So in that protocol, it defines the mail message format. There are two parts only. The header containing a number of header lines, specifying who the receiver is, who the sender is, and what is the subject of the communication. In the body, very simple, just the content of the communication. So note again that I try to clarify. In SMTP, you see mail from. So this sounds like, following this comment, you also tell who the sender is. Rec2, after the comment, after the column, you give the recipient's email address. So it sounds a little bit like the to line in the header line and the from line in the header line, but they are actually completely different things. These go in the data part, while these go earlier, setting up a connection ready for data exchange. All right. Last video about email is to finally introduce a few of these mail access protocols. That's the protocol Bob used to fetch emails from the incoming queue. All right. And we'll spend some time talking about this protocol called POP3, which used to be very popular and still being used these days. And then we'll switch gear just a little bit and talk about the last part of email application. So we've talked about the flow of sending an email all the way from Alice to Bob, right? So mail access protocol runs here. Okay, so it's this part of the entire flow. SMTP that we talked about earlier only covers email exchange to the receiver's mail server. In between the receiver's mail server and the actual receiver, it's this protocol that's controlling. So what it does is to allow the receiver to retrieve email from its local server. There are three very popular mail access protocol: POP3, Post Office Protocol, IMAP, Internet Mail Access Protocol, and HTTP. These two, you can see that they are more specifically defined for the purpose, allowing a receiver to retrieve email. The functionality is also similar. First, the receiver needs to authenticate itself, authorize itself, and then begin downloading emails. IMAP being a slightly newer version, okay, it includes a number of other features, including, for example, we could store the email messages in a more structural way, for example, creating folders and putting certain emails in certain folders. Right. HTTP, however, is special. It's quite fashionable these days. Some of the mail service providers are asking us to use a web browser as the user agent. And then the email server there is essentially also a web server, so that it runs HTTP in the middle and treating each email as a web object. So fetching an email, fetching a web object. Okay, it's the same thing, except that the content is more specifically being emails. And take a closer look at how POP3 works. Okay, the exchanges between the client and the server. The notation is very similar to the exchange we saw earlier in SMTP. S being the server, client is C. So there's an authorization phase and then the actual transaction phase. So authorization phase you see here, the client comments very typically being declaring the username and declaring the password. So you see here in the authorization phase, server says, okay, I'm ready. Client says, I'm user Bob. So the username there is Bob. Password being hungry. All right. And server responses with either okay or negative error. It's even more simpler. All right. So okay here, okay here, okay here. Maybe with the phrase after that. And in transaction phase, this is where the emails are actually retrieved. So clients sometimes say this, list. So this is to ask the servers to tell back the list of emails there are. So this is more the index of the emails, and a lot of times just containing the file size and maybe the subject line. Right? It's only until the client begin issuing comment like this, RETR. So this is for retrieving messages. So RETR1 indicates that it's retrieving this email. So this is the index of the email, the size of the email, and there could be other information. Then the server sends back the actual content of the first email, and again ends with a period, and only one period in the whole sentence. Right? The client can actually delete an email that has already been read, or in case it's a spam. Right? So DELE, very intuitive, being the delete. Quit, also intuitive, being quitting the session. All right? So retrieve an email, server sends an email. Client delete an email, retrieve another email, server sends another email, and client deletes yet another email.
Q and then plus OK, server says goodbye. So that's an example of POP3 exchange.
All right, so that's POP3. You see, once again, comments is usually some sort of special term, special word. And the other end will reply with some sort of status word saying okay or things like that. All right. Now we move on to the third application. It's called the DNS. The first video is just to introduce what is the purpose of DNS.
Next is chapter 2.4 DNS, which stands for Domain Name System. And before we talk about the purpose of it, let's talk about identifying a person. If I tell you my social security number, my name, and my passport number, which one would you think would be easier to memorize? Well, social security number, 10 digits long. Well, the national ID of Taiwan is also about 10 digits long. You can correct me if I'm wrong. Name, Polly Huang. Passport number, don't even bring this up. Polly does not recall her passport number, as a matter of fact. So very obvious, isn't it? The name is so much easier. But that's just how human brain works. Name, form of ID, much easier. Number, form of IDs, harder, especially when it's a long sequence of numbers. Well, internet, to identify a machine on the internet, shows a similar obstacle. So hosts and routers, many of them have the IP addresses, right? But these IP addresses are even harder to memorize, maybe harder than the passports. And as you're working on the PAs, right, memorizing the IP address of the workstation, super hard. Even though you've already worked on it for a while, if I ask you to type it up, it's probably still challenging. So what we do here on the internet is to give some of the important machines also a name. For example, www.yahoo.com here is the web server of yahoo.com. So you could just type www.yahoo.com and it quickly leads you to Yahoo's website. Similarly, www.google.com, quickly we reach Google. So, hey, how does the web browser know? What is the IP address of the web browser given just www.yahoo.com? Well, that is the functionality of DNS, to identify the mapping between the IP address and the name. And let's talk about DNS more formally. So essentially, it's a database of these mappings. So lots of these IP address mapping entries. Nowadays, it's distributed, meaning there are multiple of these name servers. And there's a hierarchy actually connecting these name servers. Some of them sitting at the higher hierarchy and some of them sitting lower. What's a bit special about DNS here is if you hear me saying that, hey, a web service will need to query DNS system in order to find the mapping. So, hey, web service is already an application level service. HTTP is already the application layer protocol. So it seems that the application layer protocol, HTTP, there needs to work with DNS, which is also an application layer protocol, in order for it to operate correctly. So DNS, in fact, work with multiple of these application layer protocols, not just HTTP, all right? So name servers there would help all these application layer protocols in order to resolve names to the IP addresses. It's a very essential function. Some might argue that it's one of the core internet functions, which might sit underneath the application layer protocols instead. But now we put it in the application layer such that it's only running on the end hosts. If we need to update, improve the DNS servers, we don't need to actually go ahead into the core of the internet, all these routers to change everything. So that makes changes a bit easier. Right? So there's a very special phrase that the internet designer would like to say, which is complexity at the network's edge. What it means that if you come up with something, some function that's very essential and it could go complex, then let's put it at the edges. Let's have it running on the hosts instead of running in the routers at the core of the internet. Okay. And a good side of doing this is so that we could evolve quickly and the performance bottlenecks can be removed quickly.
All right, so the purpose of DNS is to find from a machine's hostname to its IP address, because only when you have the IP address, then you'll be able to connect to the machine. All right, in the video, there's a term called complexity at the edge. I hope that you guys all capture what the term meant. Okay, sometimes on the internet, such hostname to IP address mapping, it appears that it's a very fundamental function. It should probably be in a lower layer protocol, for example, the network layer, where routing is necessary. And routing is something that you need to know the destination node's IP address in order to calculate the best routes. Okay, so it seems that the IP address seems to be something that the network layer services will require. And DNS is probably better situated there instead of up at the application layer. But because of this complexity at the edge term or the idea, the internet architects decided to move that function all the way to the application layer for a very important reason. Because when you build some functions into the lower layers, and lower layers are actually protocols that runs on all the devices, not just the end systems, but also the routers. So if you need to change, okay, functions in such a low layer protocol, that means you need to change all the routers on the internet as well. And it's really hard to make all routers changing at the same time. That is the trouble we had moving from IPv4 to IPv6. And that migration is still ongoing after decades of effort. So complexity at the edge makes sense in a way that if you feel that there's a service that's very important, you want it run efficiently, and you think that chances high that you need to change it in the future, you move it to the application such that all you need to do is to make sure that the end systems update themselves, and that can go on with the operating system updates. So it's usually a lot easier than just changing the end system is a lot easier than changing both the end systems and all the routers. Makes sense? Complexity at the edge. Although it's a notion that appears at the end of the video, but it's so very important. And it's kind of a lesson coming from years of experience from these internet architects, okay, early architects. Let's now talk about the functionalities of DNS service. Hostname to IP address is not the only service it provides. There are 3 more. So let's hear out.
DNS services. There are multiple services actually DNS provides. First is what we've talked about, the most basic one, from the hostname to IP address translation. It does 3 other forms of translation. First is the host aliasing. So what happened often on the internet is that some hosts came with host names, but the host names could be slightly longer, indicating where it is or which one of it, number 1, number 2, number 3. Okay, so those can still be slightly harder for users to memorize. So alias name here is often cute and short and very easy to memorize. So this is where the users know the services are, such as .google.com. All right, so from alias name, DNS allow the web browser to look up what is the canonical name of the server, and from the canonical name of the server, identify the IP address through one of these mappings from host name to IP addresses. So that's how host aliasing works. Second, mail server aliasing, right? So I mean, you must have one of these, right? Gmail accounts. If your friend is sending email to your Gmail account, your friend's mail server will need to know who's your mail server. So who's Gmail's mail server? This thing actually looks very general. It's in fact a domain name, not quite a host name. So what happened in DNS is there are also these entries saying for this domain, gmail.com. Okay, all the emails destined to this domain should send to this machine, SMTP, gmail.com. This we talked about when we were telnetting to an email server to demonstrate the message exchange there. smtp.gmail.com is the actual mail server for gmail.com. So there are also this entry here in DNS service. Okay, and this is called the mail server aliasing service. Last, okay, this one is a bit tricky, but it's growingly popular. It's called the low distribution service. What it does is this: for a host name, there could be multiple IPs that map to it. So IP1, and then the same host name, IP2, IP3, IP4, and so on and so forth. Okay, what happened here is that the DNS might actually rotate, returning different IP addresses each time a web browser or an email server looks up for an entry, okay, for the particular host name's IP address. So that way you kind of rotate using different physical machines every time, and therefore distribute the load of the service. Why not centralize DNS? You heard in the previous slides, there are multiple name servers and there's a certain hierarchy behind it. So why not just one? Well, it doesn't take long. At the beginning of the internet, there's indeed just one DNS server. But it doesn't take long that we realize when the machine is off, the entire DNS service is off. And everyone on the internet, unless you can memorize the IP addresses of all these servers, otherwise, there's not much you can do. Okay, it's off. Second, every application that needs to find mapping IP address given the name, traffic needs to go there. So very high volume. It gets really busy at times. And hey, those users that are around this particular server will have short delay, but they will always be part of the world far away from a particular machine. So delay not ideal. Some could suffer forever. And maintenance, this is a tricky issue, but it is indeed a problem. There are two perspectives looking at the maintenance issue. One is that the DNS server software is growing large. When it grows too large, if you want to make just a tiny little change, you need to turn off the machine, update the code until you can put it back running, right? But all you want to do is just to make a small change. So one small change influences the entire internet. Not good. Second, it's also hard to do the maintenance, right? Because if you want to just do some testing, debugging, you have to take down the entire DNS as well. And when the software grows large, chances is higher that you need to do the testing longer, debugging longer. Not good either.
Yeah, so DNS system is so not centralized. It's widely distributed. So the next two videos are related. And it's already 11:08, so perhaps we would take the breaks now and we'll resume at 11:18. And let me play how distributed DNS system is and how the query to resolve a hostname to its IP address is done. Good? So it's 11:08, 29 seconds, and we'll take a 10 minutes break and return 11:18. All right? Good. See you later. it's 11:18, and that's resume the lecture. Okay, so now let's introduce the architecture of the DNS system. Okay, there are actually 3 levels of our hierarchy at the server end, and arguably 2 levels of hierarchy at the client end. Okay, so let's check out all the components involved in the entire DNS systems.
Therefore, DNS is not a centralized system, but rather a distributed hierarchical system. And this is how the hierarchy looks like. At the top, the root DNS servers. Second level, the .com, .org, .edu DNS servers. The lowest level, or the authoritative server level, the yahoo.com, amazon.com, pbs.org, pollys.edu, ums.edu. So what you're seeing here is, hey, .com further breaks up the namespace, and each of these server at the bottom will serve a small range of the names there are on the internet, right? So distributing the load of the name IP lookup. Now, the process of looking up the IP address in a nutshell is this. Client now wants to get the IP address of, for example, www.amazon.com. What it does is first query the top server and try to find the second level server. Query the second level server, next try to find the authoritative name server, the last level. And then from the last level of DNS servers, finding the IP address for a particular host. And let's talk about each of these name servers a bit more. At the top level, the root name servers. It's connected by the local name server. Now allow me to explain. This local name server is not in the hierarchy. This local name server is actually very, very close to the client. Typically what happens is that a whole bunch of these end hosts sitting in an ISP will be sharing one. So ISP or institutional network will set up a local name server there for all the users in the domain to send the queries. And then this local name server then will relay the queries to all these servers in the hierarchy, right? So in a way, the local name server here is the client of the name to IP lookup service. So a local name server contacts the root server first, right? The root server then will contact the authoritative name server to find the mapping, get the mapping, and then return mapping to the local name server. Now, the trick part is this. When I say contact authoritative name server, it's not like directly going from the root to the authoritative name server. There's a certain way of rerouting the query until it reaches the authoritative name server. Authoritative name server is really the one containing the name and IP mapping. Okay, the top level knows the second level. Second level knows the authoritative servers. Only the authoritative name servers knows the exact mapping. And you see here, there are not many root servers. There are 13 logical root name servers, but each root name servers now have multiple physical sites. For example, here in Tokyo, there are 5 sites, 37 sites just for the Swedish root server, etc. So there are quite a few in America, but essentially very few of these root name servers. Next, the second and the third level DNS servers. At the second level, we have a bunch of these TLD servers, top-level domain servers. They're responsible each for a different top-level domains. So top-level country domains as well, UK, FR, CA, etc. So essentially, this is the last part of the host name there. Right? And each of these TLD server is maintained by some sort of organization of public interest. Some people call them NGO. So for example, Network Solutions maintain the servers for the .com TLD server, and EduCost for the .edu TLD. At the third level, we have these authoritative DNS servers, right? So it maintains the IP host mappings. And it could be maintained by the organization itself or by a service provider if the organization is somewhat small and there are not many entries reading. Local DNS server, this I tried to introduce earlier. It does not belong to the hierarchy, 3 levels. It's very special. Each ISP or institution network will set up one, and all the clients in the institution or in the ISP will configure themselves to send all the queries to this local DNS server, which is also called the default name server. So when a host makes a DNS query, query is always sent to the local DNS server. Now, these DNS servers often carry these caches of recent translation. So whenever we get a host to IP address mapping to the local DNS server, of course, forward the answer back to the client. But in the meantime, the local DNS server also keep a copy of that, okay, for some time. And this is for the benefit that if the client is looking for the same name again, okay, same name IP mapping again, then it's conveniently already cached in the local DNS server, avoiding going all the way to the hierarchy. Right, so nice. But be careful, these entries could sometimes go out of date. So while these entries are cached locally on the local DNS server, well, the entry might have been changed in the authoritative DNS servers. Okay, although very rare, but there's a chance. So these local DNS servers, if you think about it, it works more like a proxy server. Okay, it's not exactly client, it's not exactly server, it's something in the middle, helping relaying the queries, relaying the answers. Okay, so helping forward queries into the hierarchy if there's no hit here at the cache.
All right, so the architecture overall, at the server side, you have 3 levels of hierarchy: root, TLD, and authoritative DNS servers. At the client side, of course there's client, but there's some sort of proxy there we call local DNS server. Okay, it's a little bit like in HTTP, we have HTTP client. We have also the what? The web proxy. So local DNS server works very much like the web cache in HTTP. Okay. Yeah, so on the client side, you see a 2-level hierarchy, the client, eventual receiver of the response, but there's a local DNS server there, okay, taking the query first, okay, and see if there's an entry already available. So that means the query does not need to go all the way to the server side to go through the 3 levels of hierarchy. All right, so that was the overall architecture of DNS system. Next, let's find out how the query to resolve the hostname to IP address is sent and how the reply of the query come back. There are actually 2 forms of doing the query and reply. One is iterated, the other is recursive.
So far, we've learned that there's a hierarchy in the DNS servers. Here's the top, second, and the 3rd level. And we also know that there's a proxy server there, always working on behalf of the client, sending the DNS queries. So let's try to explain further from the local server here, how the query is forwarded, okay, and eventually receiving a reply. And let's do that through an example. Okay, there's going to be a host trying to reach Gaia.cs, but before messages can go out, CIS poly here needs to find the IP address of Gaia.cs over there. And we're going to illustrate this form of query forwarding. It's called the iterated querying. All right. So what the local DNS server does is to contact the server in the hierarchy, and the server will reply with something like this: name of the server to contact. Okay, someone who might know a little bit better, but I don't have it. So messages looks like this. Root server might say, hey, I don't know about Gaia.cs.umass.edu in particular, but you may ask, hey, the top level domain server for .edu. Okay, someone knows slightly better than I do. Okay, but I do know someone who knows better. Right? So that's the general idea. And so the process goes: client here issuing query. Local DNS server now forwards the query first to the root. Root returns the IP address of the .edu TLD server. Therefore, the local DNS server could re-forward the query to .edu TLD DNS. Top DLD DNS does not know the IP just yet, but top level domain DNS does know the IP address of the authoritative DNS server, so that will be sent back. And the local DNS server sends the query the 3rd time, okay, to finally the authoritative DNS server. And finally, the IP address for Gaia.cs comes back to the local DNS server. Local DNS server forward that back to the requesting client and be happy about it. Recursive query is the second form of doing the querying. So local DNS server here will forward only to the root, okay, and not contacting DLD, not contacting the authoritative DNS server. And it will be the root's job to find out what the mapping is. And root doesn't really know the mapping of Gaia.cs.umass.edu. So he forwards the query to TLD. TLD forwards to authoritative DNS server, and finally the IP address traverse back, and root DNS server here sends back to the local DNS server. Right? Can you see an issue with this? Yeah, so this way of querying puts burden on named servers that's high up in the hierarchy. There's going to be a lot of query comes to the root, and there's going to be a lot of queries coming from the root to the TLD, although the load on the authoritative DNS server remains the same, right? So heavy load at the upper level of hierarchies, not good. Keep in mind, there are only some tens of root DNS servers, physical root DNS servers. If everyone is sending the queries always to the root, we could quickly bring down all these root DNS servers. And that's not really a viable solution. Therefore, recursive query is an option that we try to disable at the local DNS server.
All right, and that takes us to quiz 13. Okay, so this is an open-ended quiz. Okay, I don't know about you guys. Yeah, some of us at some time might be thinking, hey, it's time to get real. And I know some of you guys in the class are probably this type. You decided that this is enough college education for you. If you put your mind into it, you know how to learn things, pick things up from the internet. And you see that pet book is going to be totally better than Facebook, bigger than Facebook. It's a social net system for pet animal lovers, okay? And you use your pet's photo as the cover page, as the profile picture. Okay, so this is an example of how the pet book front page might look like. Okay, now, guys, I ask you to pretend you are the owner of pet book, okay? And you will be the CTO, and in addition to that, also CEO, CFO, COO. Now, can you structure your pet book server network such that it would direct all these pet page queries so that the server load will be balanced and the delay will be low? All right. Now, you can see that this is a very open-ended request. Okay, so let me try to be a little bit more specific. Would you prefer modeling your service after the HTTP's client-server model, or SMTP's client-server model, or C, the DNS model? Okay, and let me elaborate. Okay, if you recall how HTTP works, it's plain client request, server reply. One level of hierarchy here, one level of hierarchy here. Let's ignore the proxy server, okay, for now. Oh, wait, let me go to the, sorry, I forgot. I should move to the whiteboard space. So let me go back, yeah, so this is a quiz 13. Yeah, it's time to get real. And we are now designing the pet book, okay? We are using the pet's photo as the profile picture. And pretend that you are the CTO, CEO, CFO, and COO of the company. And I'm asking you to design the server network so that the queries will be responded timely and the server's load will be balanced. Okay. So I ask whether you would use A, B, C, which model. Okay. And I'm elaborating here that the client server, in HTTP's case, is just a flat hierarchy, one level at the client end, one level at the server end. And we'll ignore the web proxy, okay, the web cache. Now this is SMTP, where you see that the client is connected to a local server. And there's a receiving server. And of course, there's another client who will be accessing the emails, okay, from another end. So you kind of see, only focusing on the server, the SMTP part, because this is not quite as SMTP. You have two levels of hierarchy here and one level of hierarchy at the server end. But in DNS, you begin to see, yeah, there are two levels of hierarchy here at the client, but at the server end. 3 levels of hierarchy. So if I try to look at the migration of these 3 applications and how their architecture gets expanded and expanded. From HTTP to SMTP, we see that the local end architecture gets more complicated from 1 level to 2 level. From SMTP to the DNS, expands from 1 level to 3 levels. So if we abstract them out, ignore which protocol they are, you see 3 different flavors of architecture, right? A, both flat, 1 level. B, you expand the client side a little. C, on top of expanding the client side, expand also the server side. Okay, so A, B, C, which one would you prefer designing the peg book, and try to justify why? Okay, and some of you might prefer coming up with something of your own. Feel free to suggest D and specify your architecture and justify. All right. Let's go to now the score space, channel W5, quiz 13. This one is very open-ended, and it's to exercise the designer's mind. Okay, so guys, you're given 10 minutes. Think this through. All right, and let's start counting time. Wow, okay, so I see Team 7 and Team 6 are choosing C already. Probably because I ask, we want a balanced load on the server, right? A and B both just use 1 server. There's no load to balance at all. Very interesting. Yeah, let's go on. Take your time. Okay, Team 5. Team 5 is ambitious. They say that, hey, Pepbook is going to be better than Facebook, right? So the load is obviously going to be higher, and it needs to at least have more functionality. So it's obvious that the A and B won't satisfy, okay? And DNS model is closer to the demand, to meet the demand. And Team 5 is more specific, okay? That store all the pages registered in Taipei in server 1 and pages registered in Taichung in server 2. So it's kind of having servers geographically distributed to allow pages nearby to update, and which will result in shorter delay. So in a way, Team 5 here is also trying to argue how they reduce the delay, not just to balance the load. Very good. Okay, let's go on. I like this design as well. Team 16 says that, hey, they're not saying that they'll just use the A model. They say, I will start with the A model. Yeah, because at the beginning, there are probably not many users. Interesting. Yeah. Now, after we have a larger user base and there's a substantial load, then we shift to the model that's a little bit more like the DNS's model. Very interesting, isn't it, guys? Very good to see that you guys are trying to be your own designer. Very good. So we have a team saying this. I saw more teams saying that maybe we will place servers in a particular region to ensure that the delay is short for the local users. But team 13 is saying that maybe putting certain species on certain servers. So to classify the content based on the species instead of the locality. You know what? If you have a dog, would you be more interested in dog pages? Right? And probably on top of that, you are more interested in dog pages that are nearby. So in a way that the preferences is probably not only the location, but also the species. Okay, very interesting. Okay, good to see that you guys think of this. All right, do we still have time? Yeah, we have 1 more minute. Okay, I think this team is also having an interesting idea. So team 2 says, we'll use a hybrid of A and C. So it's not a migration from A to C when the business grow large. It's using both. So it's almost like there's a multi-tier server hierarchy, but once we identify which server stores the content we're querying, the communication is direct, like HTTP. Query straight to the server and back. Interesting. So there's probably a searching process to identify which server really stores the data. And then the rest of the communication will be HTTP. I think it's a little bit more, it might be a little bit like the iterated query solution in DNS, but not quite, right? Interesting. Right, guys, and the time is up. Let's see. Okay, Team 12 says the DNS system. Yeah, so obviously there's a need of having multiple servers in order to balance the load. And DNS model is the only one so far, okay, maintaining multiple servers and having a hierarchy to allow easier search distribution of the content. And Team 10, back to differ. They would choose SMTP. Two-layer hierarchy. Ah, okay. Because yeah, if there are 3 layers of hierarchy, the delay can potentially be longer because you do 3 levels of queries. Okay. I think I get the argument from Team 10, right? So 1 level of hierarchy, there's just one server is going to be a single point of failure. 3 level of hierarchy is probably a little bit too much. Can we just have 2 levels of hierarchy? Yeah, that's one possibility. HTTP and DNS. Okay. Using the DNS architecture to identify the eventual server and then HTTP to communicate with the eventual server. Very similar to Team 2's, right? All right. Yeah, I'll definitely go through all you guys' answer after the break, after the class today. Let's come back to the lecture because we are yet to finish DNS. All right. So what we have talked about so far is how DNS works, the communication part. Let's switch gear and talks about the data, the entries stored on these DNS servers, and how about the format of these query and reply messages. All right. First is the entries stored in the DNS architecture, and there are 4 kinds of entries. They kind of correspond to the 4 functions the DNS service provides.
Let's take a closer look at the entries that DNS servers are storing there. They're called the records. Okay. Well, to be more precise, the resource records. Okay. And each look like this: a tuple of 4 elements. This is usually the host name, and this is the IP address, and this is TTL, the time these entries should stay on the server. What we haven't talked about is this type. There are actually 4 of them, not many. Let's look at them each a little bit closer. So first is type A. It's the most classical one, which says hostname at the name and IP address at the value. Essentially, this is the query, and this is the answer. Querying for this host, answer is this IP address. Second type, let's go here, the C name type. What C stands for is the canonical name. So what this does is corresponding to the second service we mentioned way earlier when we started talking about DNS. So it's doing what? Alias, the name alias service. So what it does is here, the entry there, name is the alias, the Q short one, and the value is the actual name, the canonical name, the real name. So here we have .ibm.com, Q then short, easy to memorize, but the actual name for that machine should be this, server is backup to the ibm.com. Right? So value is the canonical name. Third, let's look at this type, the MX type. So this is mail service type, and this corresponds to the third service that DNS provides. Name is a domain. Value is the mail server for that domain. So name here could be gmail.com, and the value will be what? smtp.gmail.com. Straightforward. Last type we have not yet talked about. It's actually not quite the fourth service that we mentioned about DNS providing. It's actually called the authoritative name service entry. Right? So the name there is a domain, okay? But it's not the top level domain. It's usually the second level domain. The value is the host name of the authoritative name server for that second level domain. So this is for the TLD servers to store all the authoritative name servers for all these subdomains. Right? So NS type entries are mostly in the TLD servers.
All right, so that's the records, okay, how the DNS entries are called. Now, the query and reply messages. Essentially, in these queries and replies, you can imagine containing questions to get the records, and in the reply, containing some of the records.
Next, the DNS protocols messages. So the servers exchange just the query and the reply messages to each other. They are in the same format, which is exactly what I'm showing here. There are two parts though. From here and up, this is the message header. From here and down, the data part, where the actual actual entries are being carried. Now let's focus on the header a bit more. The first field is called the ID. It's 16 bits long. It is used to identify a pair of query and reply. Next, in the flags, then you identify whether this is a query or this is a reply. So this is how server know that, okay, this reply is for a query that carries the same ID. In the flags, you might also see a certain client is saying that, can I do recursive query? In the flags, you might also see certain DNS server saying, no, that's disable a recursive query. And coming from the authoritative DNS server, you might see this flag being turned on. The reply is authoritative. Right? There are four other fields in the header, these. So these are specifying the number of questions, number of answers, number of authoritative replies, number of additional informations. Now these are to serve the purpose down here in the data part, because the number of questions a DNS message can carry is variable. Now, in order for the receiver to know how many lines, how many records it reads, it looks up here to find out and reads up to this point and then to the next part. So that you will not be confusing a regular reply with an authoritative reply. Right? And next, let's focus a little bit more in the data part. Okay, so in the question fields, you will only see this, the name and type in a query. That's all. There's no value, there's no TTL. In the answer entries, however, then you see the full RR, the full resource records. Okay. Authority here carries records for the authoritative DNS servers. If you have also the full RRs, it's just that those RRs are the authoritative server RRs. Last is just additional information. I see rarely this part of the data being used.
All right, so those are the records and requesting and replying the records. Last is this. In DNS architecture, recall there's also the local DNS server. It works just very much like the web cache. And this is the DNS record cache. The local DNS server is essentially. Okay. And there's a certain caching mechanism there, which is different from what we've seen in HTTP. We use this if modified since, right, special query to make sure that the copy on the cache is still the most up to date. In DNS, They don't. They use a different mechanism. And some of the entries in the cache might be outdated for a while, until later. And how long later? There's a special term called TTL, time to live. And that is the time the cache will stay on the temporary copy of the DNS reply will stay on the local cache.
DNS servers also cache data. And this is not the first time we hear this term caching. The first time is when we were talking about web caches, isn't it? So web cache there stores web objects so we could reduce delay, we could save some network bandwidth. You see here, DNS for the same purpose also caches IP name mappings. Okay? The goal is also to reduce delay to save network bandwidth. So you see, caching is actually a very general technique for data transferring services to try to avoid repeated download. So let's go on to DNS caching. So each of these mapping will be stored at the name servers once they acquire them the first time. So these entries will be there on the server's disk for some time. So the interval is called the TTL. What it stands is time to live. So during this time, the entries stay. Once the time expires, the entry is timed out, removed, okay, from the entire disk. So an example, a local name server might store the mapping for a top-level domain server so that the local name server doesn't need to go to the root name servers a lot. Okay? Again, trying to conserve the root server's capacity. Right? And the cache entries may go outdated. This is happening when the entry is not yet timed out. But the host there is already changing the IP host mapping at the authoritative DNS server. In that case, the clients worldwide will continue to get the old mapping, the out-of-date mapping, until 2 days later. This is usually the TTL of DNS mappings are set to by default. So 2 days later, the clients get the new mapping. So that's why we don't change the hostname IP mappings all that often, because during these 2 days, your customers will have trouble reaching you. So DNS caching, this is another protocol. It's defined in this RFC 2136. And by the way, the body, the community defined all these internet protocols. Okay, writing all these RFCs is called the IETF, the Internet Engineer Task Force.
All right, so that was the end of data. And you see, if you recall HTTP, we use this if modified since way to ensure the copy is the most up-to-date. But in DNS, we no longer make sure that it's the most up-to-date. You know what? There's a reason behind these, because how frequent do we update a web page versus how frequent we update the IP address of a host name? Yeah, the frequency of updating web pages typically are higher than updating the hostname IP address mapping. That is why the DNS cache uses this TTL mechanism. And they uses typically a long TTL. So during this TTL time, in case the mapping is changed, we will be confused and will be routed to some other IP addresses that are really not the IP address of a host we intended to go to. Okay, do you like that? I don't know. Yeah, you might be a little bit concerned. I am too. So alternatively, one can use a very short TTL. And so one can probably analyze how frequent these hostname IP address mapping are updated and then set the TTL accordingly, for example. So there are always ways to get around the mechanisms that are defined in a protocol. All right, now the last video of DNS. Okay, this is to try to practice what we have learned and assume that there's a company being set up, right? When a company is set up, the network admin will need to, for example, set up web server so that it serves the web pages of the company. Set up mail server so it serves allowing the employees in the company to send emails to each other. Okay, and in order for people outside to be able to find the IP addresses of these mail server, web server, there's a DNS authoritative server that the network admin needs to set up as well, right? So this video talks about what a network admin will need to do starting a company and setting up the network infrastructure.
Now let's try to put our knowledge into use. So here the scenario is you need to set up your network for a startup, network utopia. All right, so two things you need to do. First, register your domain name with the DNS registrar. Now, being a .com, you talk to this company, Network Solution, who maintains the .com TLD server. Right? Second, you provide also the name and IP address mapping of the authoritative DNS server you'll be setting up. Okay, so there could be a couple of them just in case the first one failed, there's a backup. At this point, the registrar there, the network solution there, will try to insert two records. Okay. One is, of course, the name and IP address mapping. Second is the domain name and the host name of the authoritative server. So you see here, name to IP address is the type A, the classical one. This one here is the NS type, the authoritative type, where the TLD stores domain name and the authoritative DNS server mapping. Good. Now, back home, you need to set up a couple of these authoritative servers for sure. But inside these authoritative servers, what do you store? Well, if you want a web service, you need type A entry that keeps the name of the web server and the IP address of the web server. If you wish to have email service, then you need to set up an MX entry maintaining the mapping from the mail domain to the mail server's host name. And maybe the IP address of the mail server entry, that's another A record in the authoritative server. All right, so that's how you get your customer to see the IP address and therefore being able to visit your website.
All right, okay, so that video is very useful, okay, in case you wish to be a network engineer, administrator in the future, okay. And that concludes DNS. The next chapter is P2P. So this is the different architecture as opposed to the client-server-based model, okay. And the examples we'll be introducing here is the BitTorrent. And if we have time, we'll introduce yet another P2P application that is called the Skype. Okay. But before we start talking about P2P, let me address a question from Sam. Sam asks, isn't these three responsible for different missions? I feel like a web page can work only using one of them. So it's not exactly clear what you are asking about, Sam. I guess you are probably talking about, for example, in your own team, Ricky posted a response. You will be using HTTP and DNS at the same time. And so first use a architecture like DNS. So it's a hierarchy of the web page records. And you eventually, from the root, then find the authoritative record server. This is usually very close to where the user, where the pet owner is, because the updates can go there quickly. But then in order for an arbitrary user to find this page, right, you can borrow DNS's search, the query model, to eventually find the authoritative record server, okay? And once that's identified, you use direct HTTP-like query response between the local petbook query server to the authoritative petbook server, petbook entry server. I think that's what Ricky meant, all right? So in a way, if you think about it, the root, the TLD, and the authoritative DNS server, the root maintains several TLD. That is actually to distribute load, essentially, depending on the region of the host name. And you can tell from the domain name, the last few characters in a host name, which TLD to forward that query down, to distribute that query down. right? And from within each TLD, there are several local DNS authoritative servers that will be actually more detailed. So maybe not just the .com, not just the for example, .jp for Japan. There's more, right? .amazon, .co, .japan, and that might be all these entries might be stored in the authoritative DNS server for the amazon.co.japan. Similarly for pet book, right? It can be pollys pet.tw, for example, right? And pollys pet.tw or Taipei pet owner.tw will be an authoritative server for all the Taipei pet owners. And that is registered to the .tw pet owner TLD server. Okay, so in a way, what I'm trying to say is this: although we are borrowing these models from DNS, from HTTP, from mail, but we are really just using the concept of it. Okay, now of course, once you get for example, using that architecture there, what you get might be just the host name of the pet page authoritative server. Then from that, you would query the DNS service to resolve to the IP address. But it really depends on how you build that architecture for a user to find an interesting page. Okay, so that could involve DNS, that could also bypass DNS. Okay. Is it true that some of the RRs were also stored in our browser so that we do not need to query the local DNS server? Very interesting question, Henderson. I think so. I think at least in Windows, there's a DNS cache client, a DNS cache, and that cache will sometimes send queries to refresh the cache as well in the background. Okay, so we're actually borrowing these architectures to design our own systems. Okay. All right, I understand that we are using these architectures from the protocols, and each of these protocols have their functionality. Yeah, it can be a little bit confusing. All right, great. And you know what? It's 12:07 already. So maybe let me play this video introducing what P2P. So it's kind of at the beginning, it's a review of the P2P system and introducing the two applications that are P2P we'll talk about. But in the later half of this video, you will see a scenario Poly set up to try to compare how fast it is to send a large file over the client-server-based system versus P2P-based system. And next week, the Tuesday session, you will see we will compare the two systems quantitatively, and you will see that the P2P system scales much, much better. Okay, so this video is just to set things up.
P2P applications. To be honest, this is one of my favorite sections in Chapter 2. All right, so P2P architecture. As opposed to the very simplistic client-server architecture where we have always-on service, in P2P, there's no more always-on servers. Instead, we just have these arbitrary peers directly connecting to each other, communicating to each other. As you see, hey, these peers are very likely mobile end systems. So the connectivity there is intermittent, meaning loosely connected, on and off, on and off. And the IP addresses to establish physical connectivity can also change over time. So it's actually hard to maintain a fully connected session as a user moving around, for example, on NTU campus. So we'll talk about two applications. One is for file distribution. The other is for voice service, voice over internet service. So the application for file distribution is BitTorrent, and the other one is called the Skype, an internet telephone service. We're not going to talk about applications in video streaming, but there are actually quite a number of these video streaming systems in the early years that works in this peer-to-peer way. So for example, this one, Kankan from China, that's Mandarin Chinese, meaning take a look. It was a very well-established service. Okay, before we talk about all these P2P application examples, let's talk a little bit more about the benefit of shifting from the client-server paradigm to the P2P paradigm. Right, there must be a reason why people choosing to do P2P instead of client-server. And we're going to use an example, very simple, to transmit or to distribute a file from one server to end users. Right? Each of these users will be limited in terms of the uplink as well as downlink capacity. So look over here. This is peer I. Okay, so its uplink capacity is called UI, and downlink capacity DI. Okay, so the same fashion you see therefore for user 1, uplink bandwidth being U1, downlink bandwidth being D1, and same for user 2 and user N. The server is over here. The uplink capacity is US. Well, therefore the downlink capacity is DS, although that we're probably not needing it in the calculation. All right, so file, one big file, size being big F. So this is the setting.
All right, we'll continue the comparison of circuit switching versus P2P, comparison of client server versus P2P next week, okay? And according to the amount of videos I have to play about the P2P section, P2P chapter, it looks like that we'll be able to finish chapter 2.5, the P2P chapter, before the exam. So chances high that the exam scope will cover all the way from chapter 1 to 2.5. And in terms of the PA1 to PA3. Good. And as you can see, Golan is now Poly. That indicates that Poly is now waiting for you guys to call in to do the test run. But that's wait for 10 minutes. It's only 12:12. Let me end the stream, and then you can call in, because otherwise you'll be showing your face to the whole world. All right, good. I see Gao Bo and Bing Wei are in line there. Good. Let's hold on for a few seconds. And what I want to say about quiz 13 is this. Guys, in 10 minutes time, whatever the architecture you can come up with, of course, is a straw man. It's not going to be perfect, so it's okay. But it's important, however, that I try to stimulate you, challenge you into thinking first. And those who are interested, feel free to think further and define how you are going to architect your server for your startup in detail, and make sure it works and make sure it scales. Okay, so that's all the time we have and all I want to say. With that, I say goodbye. See you next Tuesday. Oh, I see you, most of you later, 12:20. Okay, bye.